Alright, so this video is on Lewis acids and Lewis bases, and being able to understand the difference and recognize different Lewis acids and Lewis bases is extremely critical to succeeding in organic chemistry. This will help you uh, as you try to decipher mechanisms and as you progress through the course. So this is an important aspect that's from Gen Chem, but still is very, very important for organic chemistry. So in a sense, you can almost decipher any and all mechanisms, or at least figure out where to start, if you have a good handle on Lewis acid, Lewis base theory. So first, let's just give some general definitions. So what is a Lewis acid? And very general, basically a Lewis acid is a substance that can accept electrons, right? So in particular, we're looking at something that can accept a lone pair or can accept a negative charge, but in general, let's just say it is a substance that can accept an electron pair. And then conversely to that, a Lewis base is then therefore something that can, in a sense, donate or give away a pair of electrons. So when thinking about Lewis bases, one of the things that you should automatically sort of ring true in your head is you should think about lone pairs. Right, so things that have lone pairs are Lewis bases. Likewise, things that are Lewis acids typically have a vacant p orbital, right, or some vacant orbital that allows for them to accept these lone pairs of electrons. Oftentimes, these things can have partial positive charges as well. So Lewis acids, being more direct now, Lewis acids must have a vacant orbital or some sort of polar bond to a hydrogen so that it can actually donate a proton. So you must have this place for these electrons to go. An excellent example of this would be boron, right? And so we'll get to that in just a minute. A proton, H plus, right, has vacant orbital, so therefore it is also a Lewis acid. So this is probably one of the more common ones. You've probably heard of this before. So H plus serves as a Lewis acid. Also, metal cations can serve as Lewis acids, and so things that are common are like magnesium, lithium. Those guys are typical, and they're very common in serving as Lewis acids as well. The other one that I briefly mentioned earlier are those compounds that are made up of group 3A elements. So if you look over, that's those guys that starts with boron, goes down to aluminum. Also, gallium can also be in there. But things like BF3 or AlCl3, these are all very strong Lewis acids, and they're commonly used in organic, and you should be able to recognize these as Lewis acids as well. There are also some other ones that are made up of transition metals. So transition metal compounds serve as Lewis acids very commonly. And so just a few of those are like FeCl3, iron trichloride. You can have others that are, for instance, titanium tetrachloride, and also a few others would be something like zinc chloride and tin chloride. These are all very common Lewis acids that are made up of transition metal compounds. Now, Lewis bases. In general, Lewis bases are those that have some sort of non-bonding electrons or some sort of electrons to give away. And so very commonly in organic, you'll see that nitrogen and oxygen typically serve as Lewis bases. Both have lone pairs of electrons. Nitrogen has one lone pair, oxygen has two. And so they can donate those lone pairs in a Lewis acid Lewis base reaction. So here is an example of oxygen donating one of its lone pairs to a proton, which is from hydrobromic acid, and you can see that this Lewis base to Lewis acid reaction, where the proton is a Lewis acid, right, forms the hydronium ion, which is what you see what happens with acid in water. Nitrogen also serves as a very good Lewis base. It has these lone pairs, right? And so we can also react it with a proton, another Lewis acid here. And so these are just varying ways of representing these different protons. And so you can see that here we have the ammonium ion, which is the result of a Lewis base to Lewis acid interaction of the lone pair with the nitrogen that is there. Sulfur can also act as a Lewis base. It has two lone pairs just like oxygen. It's just below oxygen on the periodic table. And so it can also do these very similar things just like oxygen. So again, I want to make a point to be a bit more general here, and that is that anything that has these electrons that are available, right, that can be donated in a sense, right, these are going to be Lewis bases. So it's important for you to remember to be able to recognize these different ones. And again, we're looking for these lone pairs or some sort of electrons that are present there to allow us to donate them as a Lewis base. Now, one thing you have to be careful of, though, is that some compounds can be both Lewis acid and a Lewis base depending on their conditions. So for instance, here is just a carboxylic acid, and if you treat a carboxylic acid with a base, which in this case is serving as a Lewis base, right, it can deprotonate the carboxylic acid and protonate the base. So this is a Lewis base reaction, but a carboxylic acid can also be a Lewis acid because the oxygens there have lone pairs. And so if you treat a carboxylic acid with a strong acid, these lone pairs can come over here and grab the proton, and these can then, in a sense, allow for the oxygen here to act as a Lewis base. So it's important to understand the different conditions. So here on the bottom we have a Lewis base reaction where the acid is acting as a Lewis base, the carboxylic acid that is, and on the top it's acting as a Lewis acid, giving away its proton. So let's look at some other specific examples to kind of show you. So here is diethyl ether that you can see here. It has two ethyl groups that are on it, and we have this oxygen, so it's in a similar sense to water, except for it just has ethyl groups. And so if we treat this with BF3, then what you can see is a Lewis acid base reaction that goes on here, and the lone pair on the oxygen will then bond to the boron. And notice that boron typically has 3 bonds, and once it gets another, it's going to gain a negative overall charge. And so now what we see is we have this Lewis acid base complex here. And in this case, again, of course, the diethyl ether is acting here as your Lewis base, while the BF3 is acting as your Lewis acid at this point. Another example would be if we use acetone, for instance, and we treat acetone with an acid, and the acetone here, the lone pairs on the acetone can go and grab the proton on HCl, and so this would be an example of acetone acting as a Lewis base. Right? This is another one of those that you have to watch out for because remember, oxygen in this case can also act as a Lewis base, or it can allow for something else to act as a Lewis acid. So how can acetone, if there's no acidic proton there, act as a Lewis acid? One of the things that you have to watch out for are resonance contributors. And so if you look at acetone, you can see that we can draw a resonance structure where the electrons are pushed onto the oxygen there, giving a positive charge on the carbon. So what this means is that there's a partial positive there at the carbon, and so now something that has electrons, right, so can act as a base, and this can go and attack the partial positive there, or the positive portion of the resonance contributor. And so this is how acetone itself can also act as a Lewis acid. So it's important that you recognize different situations and uh, different aspects of how these guys react in order to be successful. Hey, thanks for watching. Hope this helps.